Hello class, welcome to this video on AP Statistics Lesson 7.2 Practice. So we're going to start with the multiple choice and work our way to the free response. So number one, it says a popular board game uses a fair 20-sided die with numbers from 1 to 20. A player conducts 200 trials. In each trial, they roll the die 10 times and record the number of rolls that result in 15 or higher. And what type of distribution has the player generated? Okay, so if you're coming from, chapter 6 where we did those other distributions, this would make more sense. So here you have this die from 1 to 20, and you're rolling it. Now for each trial, they're just rolling it 10 times, right? So you just got to be careful. They're just doing 200 trials, but for each individual one, you have 10 times that you're rolling the die. Okay, so we're just going to focus on each trial, okay? Not the number of trials. Um, so, okay, so for example, if you had a graph and had a bunch of dots, right? Well, each dot will represent the number, each dot will represent 10 times roll the die, right? 10 die rolls, okay? And then looking at the 15 or higher. So number 15 or higher. Okay, so we want to make sure we understand that. Now we're looking for specifically a specific result of 15 or higher, which means that we're looking for a criteria of success. Okay, so that means in this distribution you have either 15 or higher or you do not, and so that's going to be a success or failure, right? So that would be like a binary situation. You also have that the die rolls are independent. Okay. And for just looking at one dot, we have we have 10 die rolls. Okay, so for one individual dot or trial, we have 10 die rolls, and we're looking for success of 15 or higher. Okay, and each die roll is independent. So we have binary, we have that's independent, and we have the number, um, which is in this case going to be 10, and then the probability of success in this case. So the probability of success is got to be the same. And what's the probability of success here? Well, what's the probability of getting a 15 or higher, right? That's what we're looking for. For an individual trial, the probability of getting a 15 or higher, if you look at a die with 20 numbers, right? It's 15, 16, 17, 18, 19, 20, right? So that's going to be 6 numbers out of 20. Okay? So we're looking at, again, we're looking at an individual dot, 10 die rolls, 15 or higher. So this represents a binomial distribution. Then we're just repeating that 200 times in order to get the graph of the binomial distribution. Okay, so hopefully that makes sense. So you don't want to get confused the fact that you have 200 dots. We're looking for individually 10 die rolls per dot, and we're just simulating that multiple times. Okay. So in this case, we do have a binomial distribution based on what they're saying here. Um, and and we notice that we have 10 die rolls and the probability of success is 6 out of 20. Okay, you gotta be careful of that. Be careful with the 200, as I mentioned earlier. We have 200. You can think of the capital N of like being 200, which is like the number of simulations, if you will. Um, but the number of individual, in this case, die rolls, right, of that object is 10. Okay, so just be careful with that. Very easy to mess that up too. All right, so number 2, which of the following combinations of sample size n and population proportion p would yield the smallest standard deviation for the sampling distribution of the sample proportion p hat? Okay, so we're talking about the standard deviation, right, for p hat. So the standard deviation for p hat is the square root of p times 1 minus p over n. Okay, so then we want to figure out which one is going to lead to the smallest here. So obviously we don't want the n to be, if you look at the formula, we don't want the n to be small, because if the n is small, it's going to be a larger fraction. If the n is larger, then it's going to be a smaller fraction, and we want it to be small, right? So if I were to compare these directly, I wouldn't choose A or B because they have the same probabilities, but they're smaller n's. Okay, so we're definitely not going to choose A or B. And then obviously, if we want the smaller standard deviation, we want a small p, right? So we want p to be small, and then n to be large, so that way the sigma p hat can be small. Okay, so that leads to that. Um, all right, so in that case, the best choice would be a small p, 0.10 is the smallest, and then a large n, so it's got to be C. Okay. Okay, it's almost pretty quick. Number 3, a random sample of 30 registered voters aged 35 and older is selected, where 43% plan to vote for a candidate running for mayor. A separate random sample of 50 registered voters aged 34 and younger is selected, where 15% plan to vote for the candidate running for mayor. Political analysts consider the sampling distribution of the difference in sample proportions. Is the distribution approximately normal? Okay, so we're looking for approximately normal according to large counts condition, and we're talking about difference in sample proportions. Okay. Okay, so let's go ahead and do that. So we have basically two groups. You have the younger group and the older group. Okay, so it says age 35 and older, so there's 30 of them and 43%. And then we have 50 for these guys and 15%. Okay, so that's going to be number 1. This is going to be number 2. Okay, so let's go ahead and do that. So we got, remember, the condition for the large counts is that n1 times p1 is greater than or equal to 10. N1 times 1 minus p1 is also greater than or equal to 10. And then we have to do that for n2 as well, okay, for the second population. Okay, so we have 30 registered voters times 43%. Okay, we get 12.9. Okay, so 12.9, which passes. Now, if that passes and I do the 1 minus version, the 1 minus version is 57%. That's definitely going to pass. Okay, we don't even have to calculate that. If it passes for this, it's going to pass for that. So far it's good for the older group. Now let's do the younger group. So there was 15 of them, or no, 50, and 15% we're planning on it. Okay, so 15% of 50 is 7.5. Ah, okay. So that's not greater than or equal to 10. So it fails. So it looks like the younger age group fails. Okay, so not yes, not yes. No, the sample size for the older group is large enough. Okay, that's good. Sample size for the younger group is not. Okay, that's correct. The younger group is where it failed. All right. So number 4, a study found that 19% of financial transactions in the year 2000 were made by writing a check. In the year 2023, the percent of financial transactions made by writing a check was 4%. Based on these percentages, which of the following is closest to the probability that the difference in proportions between a random sample of 100 transactions from 2000 and random sample 250 from 2023 is greater than 18%? And we want to do 2000 minus 2023. Okay, so we're basically doing, this is going to be P1, and then this is going to be P2. Okay, so this is going to be number 1, this is going to be number 2, basically. Okay, so number 1, number 2. Number 2 is 2023. So they want they want the probability that P hat 1 minus P hat 2 is greater than 18%. So 0.18. All right. And so in order to do that, we need to verify that it's a normal distribution so that when we calculated it, we can use the normal distribution calculations here. Okay. So we're gonna do that real quick. And then we're going to verify the 10% condition. So the 10% condition states that, well, you can use the standard deviation formula if you satisfy the 10% condition. Okay, so the 10% condition, real quick, just kind of run down here. So 100, so for 10% condition, 100 is likely going to be less than 10% of all transactions for 2000, for the year 2000. And then we can say 250 is also likely to be less than 10% of all transactions. These are all financial transactions, okay, made by writing a check. Um, all right. Okay, in the year 2023. Okay, so we're assuming that, so that means we can use a standard deviation. We're also assuming large, or well, we're also going to verify large counts. So here we have 19%, so that's going to be P1 or P hat, or yeah, P1, and then we have our N1, and then we have N2, and we have P2. Okay, so we're going to do N1 times P1, so 100 times 0.19. That's 19, which is greater than or equal to 10. We don't have to check for, well, we know that the 1 minus 0.19 is automatically going to be greater, because if it's greater for that, it's going to be greater for this one. So we can just check the next one. 250 times the probability was 0.04. So we have to verify that. 4% of 250, well, 1% of 250 is 25. So it's automatically going to pass, okay? And if it passes for that, then it should pass for 96%. Okay. All right. So it's approximately normal. And because it's approximately normal, we can do a normal distribution. I'm not going to label every single thing on this. I'm only going to label the mean and, the mean. So let's find the mean. So the mean of this distribution, p hat 1 minus p hat 2, is simply p1 minus p2. Okay. Now p1 minus p2 is 19%, 0.19 minus 4%. Okay, so 0.19 minus 0.04 is 15%. So we're going to put that right here. Okay, and then we are looking for this to be greater than 18%. Okay, so we'll say this is 18%. We want it to be greater than. All right, there's my graph in general right there. And we can do the z-score. We can do the standard normal distribution or the calculator function. So we're going to do normal. Okay, so we're going to use the normal CDF function. Okay, so if this is multiple choice, I would suggest using the normal CDF function rather than having to do the z-scores. Okay, so normal CDF, and then we got our lower limit is 0.18. Our upper limit is a really large number, infinity, so 1,000. Our mean is 0.15. Standard deviation. Now we haven't done the standard deviation, so let's do that. We can do the standard deviation because we satisfy the 10% condition. So let's calculate the standard deviation. So sigma p hat 1 minus p hat 2. Okay, so the formula for that is p1, 1 minus p1 over n1, plus p2 times 1 minus p2 over n2. Okay, we know these numbers. P1 is 0.19, 1 minus 0.19 is 0.81. Sorry about that. And N1 is 100. And then P2 is 0.04. 1 minus 0.04 is 0.96. Over, it was was it 50? Oh, 250. Okay, so it's going to be 0.041, and we'll put, so then the standard deviation is 0.041 right there. Okay. All right, so let's show you this on the calculator. See what we get. Okay, so let's go ahead and do this. So we're going to hit second, bars, go to normal CDF. Oops, I took that in the wrong one. Let me go back. Normal CDF is option number 2. Wait, that's not, for some reason giving me the wrong one. Okay, so option number 2. Okay, so then the lower is 0.18. Upper is 1,000. 15.041. All right, and then we'll figure out what that is. So it's about 0.232. Okay, 0.232. All right, and so the closest answer to that seems to be B. Okay, so the answer is B. All right. So let's look at the free response. So according to the Education Data Initiative, 7% of college students receive scholarships. Suppose this claim is true. Researchers selected a random sample of 200 college students and recorded the proportion of students in the sample who received scholarships. Here's a simulated sampling distribution of p-hat. Okay, so they give you the sampling distribution over here, and they're asking what does the dot as 0.03 represent? Okay, well they said that we selected a random sample of 200 college students, right? And then recorded the proportion who received scholarships. Okay. All right, so in this case, what we have is a dot that at 0.03 that represents the 200 students, right? Where the proportion that who received scholarships is 3%, right? So we're going to write that down here. So it represents for one sample of 200 college students. The proportion who received scholarships is 0.03 or 3%. Okay, so then what is the shape of the sampling distribution of p-hat? Okay, well, it does appear to be normal, just looking at the data. However, it appears to be approximately normal. We can verify this also by using the 10% condition. Okay, so we're going to say that in this case, the 10% condition n times p, which is, we got 200 times 7. Was it, what was it? What was the percentage here? 7% was the proportion, right there. Okay, so 7% of college students receive scholarships in general. Okay, so that, which is 14, which is greater than or equal to 10. And then, of course, you have the n times 1 minus p. So 200 times 93% is 186, which is greater than or equal to 10. Okay, so it's approximately normal. As it passes the large counts condition. Okay, so what is the large? Well, hold on, let's see. So the large counts. Sorry, let me fix that. So what does the mean of the sampling distribution of p-hat? Interpret. So the mean of p-hat, remember, is just simply the mean. Or I'm sorry, the proportion, not the mean, the proportion. Now the proportion they already told us is 7%. Okay, so the mean of the sampling distribution is 7% or 0.07. Okay, so this means we're going to interpret that. So for many scholarships, so if we repeat this process or samples, sorry, many samples, In this case, we have a sample size of 200. So for many, many samples of 200 students, right, college students, the sample proportion, or the, I guess you could say the average proportion. So let me do that and write that down. Sorry about that. The average proportion, because we're talking about mu. So the average proportion of college students who earned scholarships or who received scholarships is 0.07. Okay, so that's the average. Many, many samples. You keep doing this, it's going to approach that average, which is 0.07. Now, what is the standard deviation of the sampling distribution, and then interpret it? Okay, so the standard deviation of p hat is the square root of p times 1 minus p divided by n. And we know p is 0.07. So 0.07, 1 minus 0.07 is 0.93. And what's our sample size? We had 200 college students. All right, so we'll calculate that. And we get about 0.018. All right, so 684, many, many samples of size 200. Okay, the sample proportion of college students receiving scholarships typically varies by 0.018 from the mean, or from the from the mean, or the true proportion, right, of 0.07. Okay, so there you go. So that's that. And then part E, what condition must be met to use the formula for standard deviation? Okay, so that's the 10% condition. Okay, to be able to use standard deviation formula, we have to assume the 10% condition. Okay, so the 10% condition, and we're assuming that the 200 is less than 10% of all college students, which is true. We can assume that that's true. Okay. All right. So the next one. Number 6, for each of the following scenarios, determine if the sampling distribution of p hat is approximately normal. Be sure to justify. All right. All we got to do is just verify the large counts condition. That's all we got to do for this problem. Okay. Okay, so let's go ahead and verify. So for this one, we got 10 times 0.0 or times 0.4 is equal to 4, which is not greater than or equal to 10. So we can see that it fails. So we only have to do one of them and it automatically fails. So no for this one. So not approximately normal. And then the next one is 30 times 0.4, which is 12, which is greater than or equal to 10. Now, if I do for 1 minus 0.4, then it's going to also pass. Because if it works for 40%, it's going to work for 60%. Now, this is going to give you 18, which is greater than or equal to 10. So, yes. And then next one, 100 times 0.4 is 40. And then 100 times 0.6 is 60. So then it checks. So, yes. All right, what values of n make the sampling distribution of p hat more normal? So this is just for part B in general, what we want to look for. So basically, they're just kind of wanting you to understand that here the first one is a no, the other ones are yes. So as you increase the sample size, it's going to allow it to be more normal, and that's what they're wanting you to understand. Okay, so sampling distribution of p hat is approximately, or is more normal, I guess you can say, when n increases, when sample size n increases. Okay, so that's that one. And then C, looks like they want you to check that as well. All right, so 50 times 0.06 is equal to 3, which is not greater than 10. So that's going to be no. 50 times 0.48. So notice that the sample size is now being the same. They're adjusting the P so we can see if there's a relationship going on here. Okay. All right, so let's do, this should be 24. Okay, yeah, it's 24, which is greater than or equal to 10. And then 50 times 1 minus that is 26. So yes. And this one is 50 times 0.96, which is going to be 48. And then 50 times 4% is going to be 2, which is not greater than or equal to 10. Okay, so that's a no. And so they're asking, okay, so we got 2 no's and a yes. What values of P are going to make the sampling distribution more normal? Well, we don't want P to be too extreme. So notice this is extreme, this is extreme. And we want P to be closer, to be more moderate in value. So more closer to 0.5. The closer it is to 0.5, the more normal it's going to get. If it's closer to 0.06, if it's closer to the extremes, to 0 to 1, it's going to be skewed. And it's not going to become normal. The only way to make it normal is if you have a really, really large sample size to offset that extreme value of P. Okay. All right, so let's go ahead and describe that here. So the sampling distribution of P hat is more normal as P approaches 0.5 and is less normal for extreme values of P, i.e. close to 0 or 1. Okay, so number 7, a local newspaper is planning to select a random sample of community members to determine what proportion of the community supports a proposal on the upcoming election. Suppose 64% of the community supports the proposal. Assume there are at least 10,000 community members. What condition must be met in order to use the formula to calculate the standard deviation of the sampling distribution of the sample proportion in this setting? All right, so the condition for this to be able to use the standard deviation is a 10% condition. Okay, so the 10% condition. This is when the sample size is less than 10% of the population. Okay, if that's true, then we can use the formula. So now we want to say calculate the standard deviation of the sampling distribution of the sample proportion. So let's verify the 10% condition first. The sample size here is 10. Assume there are at least 10,000 community members. Okay, for this. Okay, so and our sample size is 100, right? So 100 divided by 10,000, and this is at least 10,000. So that's our at least 10,000 as our population. So in that case, this is going to be 1%, which is less than 10% of the population. Okay, 10% of all community members. So that's checked. So now we can calculate the standard deviation. Okay, so standard deviation p hat is the square root of p times 1 minus p over n. So it's the square root of, and p is 64%. So 0.64 times 1 minus 0.64, which is 0.36, over n, which is 100. All right. Okay, so here you should get about 0.048. All right, part C, calculate the standard deviation of the sampling distribution of the sample proportion for samples of size n equals 400. How does this standard deviation compare to the one for n equals 100? Okay, so let's do that here. So sigma p hat for 400 is, so now the only difference is that we're going to put 100 or 400 on the bottom. Okay, so 0.64, 0.36 over 400. So if you calculate that, you're going to actually get 0.024. And if you were to compare it, it's half as large as the sigma p hat for n equals 100. And the reason is that the greater the sample size, the lower the variability. Okay, and that you can see that in the formula. Okay, so the next one is part D, calculated. Okay, so now we're doing for n equals 900. Okay, so the result is going to be 0.016. And notice that if I were to times that by 3, that would give me 0.048. So I got 0.048. If I divide that by 0.016, that's a factor of 3. So it's 3 times as small. Okay, so it's 1/3 of the sigma p hat for n equals 100. So you're starting to see a pattern here. So how does the standard deviation change when the sample size is multiplied by some value k? Well, the standard deviation changes. Okay, so when the sample size is multiplied by some value k. So for in this example, when it was 400, right, it was 4 times 100, right? So 4 times 100. So in that case, k was 4, right? And the standard deviation, notice, for 400 was half as large, right? Was half as large. Okay, so that means so there was a factor of half. So it appears to be like 1 over square root of 4 is 1/2. So it's 1 over square root of k. See that? All right, so that's how you can tell. So if we wanted to do this formally, well, all we have to do is we know that sigma p hat is the formula that we wrote down earlier. But if I were to adjust it, let's put new, that by multiplying by some factor k, right? So how does that affect it? Well, if I pull out the k, it pulls out as a square root. So 1 over square root of k, just to do a little algebra. And now we know that this is equal to that, right? So, which is sigma. You can replace that with sigma p hat. So we get 1 over square root of k sigma p hat. So you can see that we just have to divide by square root of k, okay? So the standard deviation is multiplied by 1 over square root of k. All right, so you can see that there. So let's look at number 8. All right, the National Center for Education Statistics reports that 18.8% of public schools require students to wear uniforms. A curious high school student wants to investigate this claim and plans to select a random sample of 80 schools and then calculate the proportion of these schools that require students to wear uniforms. Assume that the 18.8% claim is true. So describe the shape, center, and durability of the sampling distribution. Okay, so let's look at the shape. We want to look at the large counts condition. Okay, so remember it's n times p, right? So here we have n, and then we have our p. So let's verify that. So 80 times 0.188 is 15.04, which is greater than 10. And then 80 times 0.812, that's 1 minus that, is 64.96, which is greater than or equal to 10. Okay, so we got that. So it's approximately normal. Okay, so now let's look at the mean. Okay, so the mean is easy. It's just going to be p, which is 0.188. Okay, sounds pretty easy. Standard deviation, we'll need to calculate that. So sigma p hat, remember it's p, 1 minus p over n. So it's going to be 0.188. 1 minus that is 0.812 over 80. And upon calculating that, you should get 0.0437. Okay, there you go. Those are the three things. The student finds that 12 of the 80 schools, or 15% selected, require student uniforms. Use a normal approximation to find the probability that the student would get a sample proportion of 0.15 or lower if the 18.8% claim is true. Okay, so we're going to use a normal approximation. So we know it's a normal distribution. Again, if it's normal and in the middle is 0.188, and he got 15%, which is 0.15, right? This is what he got. What's the probability of getting that or lower is what they're asking for. Okay, so if that probability is high, then that means that there's no, we don't have convincing evidence that of against the claim. If it's less than 5%, right? That's our cutoff. Then we have convincing evidence to against their claim that it's 18.8%. Okay, so just to give you an idea. So let's calculate the probability. So the probability that your p hat is less than 0.15 or equal to. In order to do that, we're going to do the normal CDF function. Okay, so normal CDF, the lower value is 0.15, lower value is negative infinity. Okay, so according to this region, right? Negative 1,000. Our upper is p hat, which is 0.15. Our mean is 0.188, and then our standard deviation is 0.0437. So then if I calculate that, you should get 0.1923 approximately. All right, so notice that 9.1923 is 19%, which is greater than the percent that they're asking for, or it was greater than the cutoff, which is 5%. Okay, so I'm assuming they might ask about that. Okay, so they didn't. But if they did ask, right, you would say, okay, well, because it's 19%, it's greater than 5%. It looks like there's evidence. There's not convincing evidence against the claim. Okay, so it says use a binomial distribution to find the probability that the sample of 80 schools would have 12 or fewer that require students to wear uniforms if the 18.8% claim is true. Okay, so we're going to basically compare this. We use a normal distribution here, but what if we use the binomial distribution, right? For 12 or fewer schools. Okay, so let's, in order to do that, we need to use the binomial function, right? So it's 12 or fewer, so the probability that x is less than or equal to 12. So because it's less than or equal to, we can use the binomial CDF function, okay? Binomial CDF, remember, is for less than or equal to. Binomial PDF is for equal to, okay? So you got the binomial CDF function, and then you're going to plug in your n, which is 80, your p, which is 0.188, and then your x value, which is 12, right? 12 or fewer. And you get 0.238, okay? So about 20 something percent here, about 20%, about 24% here, about 20% here almost. Okay. All right, so let's look at number 9. In a recent report, Gallup determined 32% of employees in the United States, okay, so that's P, are considered engaged employees, meaning that they're highly involved and enthusiastic about their work. Suppose a very large U.S. company, so very large, okay? So it's a random sample of 50. All right, so assuming the Gallup poll claim is true for this large company, what is the approximate probability that the sample proportion will be greater than 0.46? All right, so first off, we need to see if it's a normal distribution. Okay, so we're going to do the large counts condition and say, okay, 0.32, or the sample size of 50 times 0.32 is, in this case, is 16, which is greater than or equal to 10, so that's good. And then 50 times 1 minus that, or 0.68, is 34, which is greater than or equal to 10. That means it's approximately normal. All right, so we can use the normal distribution to get this probability. We also need the 10% condition in order to use the standard deviation, okay? The 10% condition. And so we're saying that 50 is less than 10% of all employees in very large U.S. company, okay? So that means we can calculate the standard deviation, okay? So we're going to do that. Well, I'll just do it over here. So standard deviation is square root of 1 minus, or p times 1 minus p. So p is 0.32 times 1 minus p is 0.68. Divide that by the 50. So the standard deviation is should be 0.066. Okay. All right. And let's go and get the mu while we're at it. The mu is pretty straightforward. Okay. So the mu is simply p, which is 0.32. All right. So we have we have space here, by the way, down here. So, but I'm just gonna, yeah. So I'll just do continuation of A. Okay. Here, because we have room. Okay, so this is p hat graph, and so we got 0.32 in the middle, and then it goes by 0.066s. I'm not going to do all the numbers. I'm just going to do what we want. We want it to be greater than 0.46. Okay. All right. So the probability that p hat is greater than 0.46. We're going to use the normal distribution function. So normal CDF. The lower is 0.46. The upper is 1,000. The mean is 0.32, and the standard deviation is 0.066. So if I do that, I get approximately 0.017. Again, if you don't want to use the calculator method, you could use the z-scores. So let's talk about how we would calculate z-scores, okay? Just in case. So if I wanted to calculate the z-score, remember the z-score is value minus mean over standard deviation, okay? Now the value here is the p hat, right? The mean is mu p hat, right? But mu p hat is equal to p, right? So we can just replace that with p. And then the standard deviation is just a sigma p hat, okay? So there you go. So that's your that's how you calculate your z-score. All right, so our p hat is 0.46 minus our p is 0.32 over the standard deviation 0.066. Okay, so let's calculate that real quick. So it's going to be 0.14 divided by that. So 2.12. Okay, so about 2.12, 2.12 is our z-score. Now, then to calculate the probability that z is greater than 2.12, right, because it's the area to the right, we have to do 1 minus the probability that it's less than. Because remember, the table gives us the area to the left. If I want the area to the right, I got to subtract from 1. So let's look up this on the table, the table that comes with your AP tables here for AP exam. So you got 2.12, 2.12, okay, which is 0.9830. Okay, 0.9830. But if I subtract that, I get 0.01, 0.01, yeah, 0.0170. Okay, all right, which is exactly what we got there. Okay, so just want to show you a couple ways to do that. All right, number 10. French is the first language for 88% of the population in France and for 20% of the population in Canada. Suppose a random sample of 200 people in France is selected and the proportion in the sample who speak French as the first language is calculated. A separate random sample of 300 people in Canada is selected and the proportion in the sample who speak French is calculated, p hat 2. Here's a sampling distribution of p hat 1 minus p hat 2. So we get the difference in sample proportions. We have we'll call that, so it's, so it looks like French is 1 and then Canada is 2. Right? So this is going to be P1. This is going to be P2. Then we have N1 and we have N2 here. Okay. Okay. So what does the dot about at about 0.747 represent? So this one right here. Okay, so remember, when they did this, each dot, they're looking at a random sample, right? So a random sample of 200 people in France, and then another random sample of 300 people in Canada, and then they're taking the percent who speak French, and then they're subtracting those. Okay, so that's what that 0.747 represents. Okay, so for one random sample, because there's only one dot there, so for one random sample of 200 French. Well, I guess you could say, well, I don't want to get confused. 200 people in France and 300 in Canada. The difference in proportions who speak French as the first language is 0.747. Okay, so what is the shape of the sampling distribution of p hat 1 minus p hat 2? Okay, so in order to do that, we need to do the large counts condition. So we're gonna do this for number 1. Remember, it's n1 p1 and then n2 p2 and all that stuff. Okay, so let's do the n1 p1. So n1 is 200, p1 is 88.88. Okay, so 200 times 0.88 is going to be 176, which is definitely greater than or equal to 10. 200 times 1 minus that, which is 0.12, is going to be 24, which is greater than or equal to 10. All right. Even though the p is extreme, the sample size is large enough to offset that, so that's good. And then we have the next sample. It was how many? It was 300 in Canada. And the percent was 0.20, which is 60, which is definitely greater than 10. And then 300 times 1 minus that, 0.80, it's going to be 240. So therefore, it's approximately normal. All right, so what is the mean of the sampling distribution of p hat 1 minus p hat 2? Okay. So the mean of p hat 1 minus p hat 2, the formula for that is p1 minus p2. And so all you got to do is you're going to take the proportion in France that speak French as their first language minus the proportion for Canada, which is 0.20, and you get 0.68. Of course, we want to interpret that. So, okay, so let's interpret that. So for many random sample pairs, we're pairs because we have two populations here of size 200 for France and 300 for Canada. The average difference in proportions who speak French as first language is 0.68. Okay, so what condition must be met to use the formula for standard deviation? Okay, so it's the 10% condition. And we're going to go ahead and check the conditions. So we got to check it for all of them. So there's 200 people in France that they selected. That's less than 10% of the population in France. Okay, of all people in France. Okay, and then the next one is 300 is less than 10% of all people in Canada. Make sure the book uses. Okay, so what is the standard deviation of the sampling distribution of p hat 1 minus p hat 2? Interpret. Okay, so the standard deviation, let's calculate that. So standard deviation of p hat 1 minus p hat 2. So the formula for that is p1, 1 minus p1 over n1, p2, 1 minus p2 over n2. Okay, so we got p1 is 0.88 times 1 minus 0.88 is 0.12. And then we had 200 people there. Okay. And then this one was 0.20. 1 minus 0.20 is 0.80 divided by N2. How many people were there? 300. Okay, so the standard deviation is about 0.033. Okay, and they want you to interpret that. So when selecting random samples, I guess you could say random sample pairs of size 200 France and 300 Canada. The difference in sample proportions who speak French typically varies by 0.033 from the mean of 0.68. Okay, so that's the interpretation of the p-hat, that on average, it typically varies 0.033 from the mean. When you're looking for specifically 200 random people from France, 300 from Canada, etc., etc. Okay, so number 11, sports cars have often been associated with the color red, but this is really the color of choice for famous sports car companies. Is it really? So according to the Italian sports car company Ferrari, 40% of Ferraris are ordered in red, while it is only 16% for German sports company car company Porsche. A curious car enthusiast used an online database to select random samples of Ferraris and Porsches that are registered in the United States. Okay, so we got the percent for the Ferrari, so we're going to call that P1. And then we got the percent for the Porsches, we're going to call that P2, okay? And okay, random sample 100 Ferraris. So there's your N1. So for a random sample of 100 Ferraris, the car enthusiast calculate the proportion of sample that is red. What are the mean and standard deviation of the sampling distribution of p hat 1? Okay. So, all right, so the mu of p hat 1 is just p1, right? Which is simply 0.40. That's it. Pretty straightforward. And now the standard deviation of p hat 1 is the square root of p1, 1 minus p1 over n1. So we're going to do that. So that's going to be 0.4 times 0.6 over 100. And that's going to be 0.049. Okay, so that's that one. And then this one is N2 for Porsches. So the mean for the Porsches, P hat 2 is just P2, which is 16% for the Porsches. And then sigma P hat 2, again, we're just going to just apply the formula. So 0.16 times 1 minus 0.16, which is 0.84. And then there were 200 Porsches selected. So 0.026. All right, and then so then now what are the mean and standard deviation of when you combine them? All right, so mean p hat 1 minus p hat 2. Notice that in order to do this, you just simply combine the mean. You basically are combining the mu of p hat 1 minus the mu of p hat 2. Right? So basically you're just combining the 0.40 and 0.16. You're using the two separate ones. Okay, which is equal to P1 minus P2, which is 0.40 minus 0.16, which is 0.24. Okay, now the standard deviation, the way that's going to work, if you remember your rules, right, for how this works, is that the way the standard deviation works is that it's the square root of the sum of the individual ones, right? And the formula for the sigma is just going to be the square root of that. But then if I take the square of that, it's just going to be P1 1 minus P1 over N1. But in any case, so this is just a tie-in with transformations back in the previous chapter. So basically, you're just going to plug in those numbers, 0.049 squared plus 0.026 squared, okay? But yeah, when you do this, you end up getting the same that formula, right? But let me just show you so you can kind of understand where it comes from. So the sigma P1 formula is P1 1 minus P1 over N1 squared. And then the formula for sigma P hat 2 is square root of P2 1 minus P2 over N2 squared. And so notice that the square and the square roots cancel. See that? Leaving you with the usual formula, which we've seen before. There you go. Okay. So that's how that works. And then, yeah, so anyways, you just plug in. Let's go ahead and plug in. I just wanted to show you that derivation. All right, so P1, oh, we've already done this. So what I'm going to do is I'm just going to plug into this part. So sigma P hat 1 was 0.049. So it's going to be 0.049 squared. And then this is 0.026. So I'm just going to do 0.026 squared. This will just make my calculation simpler. So if I do that, I get 0.055. All right, so number 12, the United States and China are the top two countries for producing revenue from video games. A recent survey found that for people aged 16 to 24, 82.9% of the United States and 72.1% in China are playing video games. Assume this claim is true. Suppose a random sample of 100 people. Okay, so let's start labeling stuff. So we got, so that's going to be P1. That's going to be P2. 100 people from the United States. So that's N1. And 100 people for China is P2. Or N2, sorry. Okay. Describe the shape, center, and variability. All right, so let's test out to see if it's approximately normal. Do we have room? Yeah, we have some room here. Okay, so let's do the large counts condition to determine if it's normal or not. Okay, so we're going to do N1, P1, multiply those. So 100 people in the US times the proportion of those in the US who play video games, 0.829. And that's going to be 82.9, which is greater than or equal to 10. And we got 100 times 1 minus that, which is 0.161, which is going to be 16 point. It should be 171. Sorry about that. Which is 17.1, which is greater than or equal to 10. All right, so that passes. Now we're going to do it for the China. So we have 100 people, and it was 72.1% in China. So 0.721, which is 72.1, which of course passes. And then we got 100 times 1 minus that, which is 0.279, 27.9. All right, so that means it's approximately normal. All right, so we're going to continue with A here as well, okay? So the mean of P hat 1 minus P hat 2 is P1 minus P2. So you're going to take the US number minus the China number, okay? All right, so then the mean is going to be, which is 0.108, okay, so 10.8%. All right, and then we'll calculate the sigma P hat 1. Well, actually, let's do it over here. Okay, so the square root of P1 times 1 minus P1. So 0.829 times 1 minus that, 0.171 over 100 people plus 0.721 for China. 1 minus that is 0.279 over 100 people. All right, so standard deviation is going to be about 0.059. Okay, so now let's do part B. A proportion, the United States is at least 10% greater than the proportion from China. Okay, so they're doing the probability that p hat 1 minus p hat 2 is greater than 10%, greater than 0.10. At least, so it could be greater than or equal to. All right. Okay. All right, so then now if we were to draw a normal distribution, which we'll do that here. In the center, we have the mu, which is 0.108, right, that we calculated. And we want it to be greater than or equal to 0.10. Okay, so that means 0.10 is here, greater than or equal to that. Okay, and that's the p hat 1 minus p hat 2. Now, we're going to show you the formula for z as well as the formula for, or as well as the calculators. We're going to do both, right? So if I were to do z, the formula for z, remember, z is value minus mean divided by standard deviation. The value is p hat 1 minus p hat 2. The mean is p1 minus p2. And then the standard deviation is, well, the sigma p hat 1 minus p hat 2, which is like this formula right here, okay? Okay, so p hat 1 minus p hat 2, that's 0.10, because that's what they have here, right? Minus p1 minus p2, we just did that, it's 0.108, that's just the mean. Over the square root, or over the, we'll just do the value, we already calculated it, 0.059. All right, and then we'll calculate the z-score for that. So negative 0.14-ish, okay? So negative 0.14. Okay, so then the probability that z is greater than or equal to negative 0.14, we have to do 1 minus, okay? Because it's the area to the right, so we have to do 1 minus the area to the left. So let's do negative 0.14 using our table. Negative 0.1 and then 4. So it looks to be about 0.4443. Okay, so 0.557. Okay, that's the table method. Now, if I were to use the normal CDF function, I need the lower, which is 0.10. The upper is infinity, or a big number, right? So I'm just going to do like 1,000. The mean is 0.108. The standard deviation is 0.059. So if I calculate that, I get about 0.5539. So really close to what we got there. So they're really close. All right. Number 13, a recent report claims that adults binge watch streaming video more than teenagers. According to the report, 70% of adults ages 30 to 44 are binge watchers, and 60% of teens are binge watchers. Assume this claim is true. Suppose a random sample of 80 of these adults are selected, and proportion who binge watch is calculated. So we have p hat a for adults, okay, so that's important. So that's NA, I guess you can call that. And here this would be PA for adults. And then they use PT for teens, so this is going to be PT, and this is going to be NT. All right, so what is the probability that the sample of adults has a lower proportion of binge watchers? Okay, so Yeah, so we're going to need to spend some time in calculating that. So let's do that over here. So first off, we need to see if it's approximately normal. Okay, so we're going to do the 10% condition or the large counts condition. All right, so we're going to do NA times PA. So we're going to do the 80 times the 0.70. Okay, so that's going to be 56 greater than or equal to 10. 80 times 0.30 is going to be 24. Okay, and that's for the adults. Now for the teenagers, we have 50 times the percent was 60. Okay, percent. So we have 50 times 0.60 is 30, which is greater than or equal to 10. And the 50 times 0.40 is 20, which is greater than or equal to 10. So it's approximately normal, okay? We will also, so we're going to continue this in part A, okay? We also want to verify the 10% condition um, for the standard deviation formula, because we want to use the standard deviation formula, but we have to make sure the 10% condition is satisfied. Okay, so we're going to say 80 adults is likely going to be less than 10% of all adults, right? Check. And then the 50 teens is less than 10% of all teens. Okay, so that makes sense. So let's check. So the 10% condition is satisfied. We can go ahead and calculate the sigma p hat and all that. Okay, so mu p hat A minus p hat T, that's what we're trying to do. Um, it says the sample of adults has a lower proportion than the sample of teens. Okay, so we want probability that it's less than. That means we want so what they want here. Let me just put it here. They want the probability that p hat A minus p hat T is less than 0. Okay, so they want the adults to be less than the teens for the probability. Okay, all right, so this is PA minus PT, which is 70% for adults, and it was 60% for teens, so it's 10% for the difference. All right, let's calculate the sigma, though. Now we can calculate the sigma because it satisfies the 10% condition here. So the square root of the adult percentage, which is 0.70, times 1 minus that, over the number of adults used, 80, plus the percent of teens that binge watch, 0.60, times 1 minus that, 0.40, over 50 teens used. Okay. All right, so the standard deviation for the teens is, or for the just for this population, 0.086. Okay, for this example here. So we got 0.10 for the mean, 0.086 for that. Okay, so now let's go ahead and draw the standard deviation or the curve, the normal distribution curve. So in the middle, we're going to have the difference, which is 0.10, the mean. And then we're going to go by 0.086s, but that's how you would set it up. But we only care about, we want it to be less than 0. Okay, so 0 is here. We want it to be less than that. Okay, so that's the probability there. All right, so let's calculate the z-score. Remember, so the z-score here is going to be as follows, just as a reminder. Minus, and then PA minus PT over sigma P hat A minus P hat T. All right, so P hat A minus P hat T, that's just 0, because that's what we wanted to find the probability of, right? And then PA minus PT is 0.10 over the square root. Oh, we don't have to do the square root formula because we already did it over here. 0.086. Okay. So negative 1.16. Okay, so negative 1.16. So then the probability that Z is less than negative 1.16 is, here, let me lasso that. I'll move it out of the way. It's too low or too high. Okay, so let's look it up. Negative 1.16 for the negatives here. So negative 1.16. So it's 0.1230. There you go. So 0.1230. There you go. That's what we're looking for there. And then let's compare that to the normal. So we're going to do the normal, the calculator. So normal CDF, the lower is negative infinity, so negative like 1,000 or something. The upper is 0. The mean is 0.10. The standard deviation is 0.086. And if you do that, you get about 0.1225-ish, which is pretty similar, okay, to what we get there. Okay. Okay. All right. So there's part A, and then I guess we have to finish part B. Sorry, I realized I didn't have enough room for part B. So I'll just write it over here. Sorry about that. I forgot that I wrote big because I forgot that we had part B to answer. Okay, so I'll answer part B over here, just for the sake of space. Suppose the two samples revealed exactly the same proportion who are binge watchers for each group. Okay, does this result provide convincing evidence that the report's claim is not true? Justify. Okay, well, we just calculated it for 0.122, or for this, and we got 0.1225. Okay, so remember the way we know we have convincing evidence is if it's greater than 5%, or if it's less than 5%. Okay, so we're gonna say no. Since 0.1225 is less than 0.05, so less than 5%. Or it's greater than, I'm sorry, greater than. Uh, we don't have convincing evidence that the claim is not correct. Okay, all right. That's going to do it for the video, guys. Hope you found this useful and informative. And as usual, I'll see you next time.